Hi everybody, this is Mark Weitzman and welcome back to my channel on YouTube channel on Theoretical Physics with Mark Weitzman. I decided to start a new playlist on computational physics. I'll make a bunch of videos on a book that I went through a long time ago, but I'm rewriting all the stuff, the programs in Python. And it's an excellent book, and I'll discuss it with you in a second. Um, to start, I'm going to start with some Jupyter notebooks. For those of you who are unfamiliar with Jupyter notebooks, they're designed in a way where you can put like text and code and latex and all in the same document. You can execute it, and it works in several languages. Mostly it's used for Python, but it also works, I think, for R, and Julia has notebooks as well, I think, although I'm not sure they're Jupyter notebooks. But, the thing about it is, like, you can click in a code cell and then just press, like, Control Enter, and it will run the code in the cell. And so, there it is, for instance. I'm just going to get rid of it for now. But just to show you an example, this is like just a test thing, but you can just go through each one and just run the code, and there's the output, and then you're in the next cell and you just go Shift Enter, and then here we'll do like a plot and then another plot. So it's very good. You can run plots, animations, graphics, and you also have text and latex code. So for instance, in my notebook, which I'm going to go through in this section, you can put actual latex in there. And so it's sort of like, it's like an online notebook or something. It's become very popular for presenting scientific material and for developing scientific material. For long programs, you can't really use it because the namespace tends to get corrupted. And anyway, I want to start with a discussion on computational physics. As many of you know, or some of you know, I have a website on scientific programming, machine learning, quantitative finance, and in the links just below the title of the description of the YouTube video, you can click more and you'll get all the how to sign up if you're not already signed up and everything. And right now I've got a bunch of things populated here, but I'm adding stuff on computational physics. And so, for instance, I've just added the PDF of what I'm going to show today. And then also, this is the actual Jupyter notebook. And I don't want to go into details on how to run Jupyter notebooks and things like that. If you want to, there's an excellent, well, it's a pretty good book. It's relatively cheap, and it's Python Tools for Scientists, and it gives you the whole thing on how to. I highly recommend the Anaconda distribution. I think it's become standard nowadays. And then JupyterLab and the Python scientific libraries. It's just a lot of pages. If you like books, you'll use it. You can just go to the documentation online or just Google online how to use Jupyter notebooks and JupyterLab notebooks. They run in a browser. Right now, when I run this, I'm sorry, I didn't mean to do that. When I'm running this notebook, it's in a browser. So let me just make it bigger. So this is in a Safari browser where this is running, and the code runs there. And it hooks up with all your Python installation, and, who knows how the technology works. But also, MITx had two, MITx Online, and you just go to MITx Online, you Google it, or they had two courses on computational data science and physics, and computational data science and physics 2, and they're adding another one soon, I think. they also use Jupyter notebooks. And even though you can't get credit for these courses anymore because they're over, I think you can access the material. And this is Computational Data Science and Physics 1. And you can, they have a whole thing on how to use Jupyter notebooks. There are various ways. You can just run them locally, or you can use like Google Colab, and you get them from GitHub or various places. And so if you want to take this course or go through this course, it's an interesting course. It's basically a lot of data science and physics and so on, but it uses these notebooks. And so going back to I have a lot of resources here. Koonin's book is an old book. It was written in the mid-'80s when I was at Caltech. I had a pre-publication version. There's a version where it was written using the BASIC language. That's actually what I own. It came with a disk and everything. And it had a Fortran version a few years later. Now you might think, why would you want to use material that's so out of date? And as I talk about, if you get my notebook, if you go here and either go to the PDF, or actually you can download the notebook and run it if you have JupyterLab installed or Jupyter Notebook installed. But the main thing is that it's really a physics book, and it's at the advanced undergraduate level. So it kind of assumes, as I say in this introduction here, that you either have a prerequisite, a co-requisite of quantum mechanics, statistical mechanics, mathematical methods, and classical mechanics. These would be your prerequisite or co-requisites, and it does some very advanced problems. Remember, this was done in 1985. Imagine an IBM PC XT. You would think, how could it possibly do this stuff? But it was able to do it. And it had good graphics and everything. And so what I want to do is to sort of reconstruct these programs. And on my website, I even have a zip folder with all the old Fortran files or all the old BASIC files. But you don't want to use that. But I want to just rerun everything in Python, and also run it faster and make it easier by using some of the advanced features of Python like NumPy and SciPy, and we'll use Matplotlib for the plotting and the animations. So in this notebook, these links are live, not on the PDF, but in the notebook itself they're live, and you can go there. This has my site. And so Chapter 1 starts with basic mathematical operations. And today I'll cover numerical differentiation. In Chapter 1, this notebook, I'll have a notebook on each chapter. After that, it does numerical quadrature, which is integration. Koonin reserves the term integration for integrating differential equations, finding roots. Semi-classical quantization of molecular vibrations is the first long example that he has, and then scattering by essential potential. By the way, these programs, both the examples and the projects, they're long programs. They'll be like 200-300 lines. In BASIC they were like 500 lines. And if you use some of the advanced Python tools, you can just write one line. You don't have to write a procedure to find the roots or to do an integration or differentiation, but it's good to understand what's going on. So, as I said, in this notebook, I'll start by using simple standard Python 3 code. I'll occasionally supplement with functions that are implemented using NumPy and SciPy. And so let's start. So I hope this is visible. Let me see if I can make it any bigger. Yeah. A little bigger. Okay. So there are these standard formulas for calculating derivatives. There's what's called a forward difference 2-point. Just your basic calculus definition. And the accuracy of order h, backward difference 2-point, and the symmetric 3-point, much more accurate. Koonin derives these. He doesn't derive all his formulas in his book, but he usually derives the easier one. Again, computational physics involves numerical analysis, programming, and physics. So you have to sort of integrate all three, and you can't spend too much time on any one area. One thing about numerical differentiation is that, at least if you use formulas like this, it's an inherently unstable process because you're taking the difference between two quantities. And this will get to be, you're subtracting one quantity from another, and when they're about equal, it can end up being zero because of round-off error and finite precision. So just to show you, I'm going to go to this box here, and I'm going to run this box. You can't see it, but I'll scroll so you can see it. So that is the output, and I'm doing a h. I'm decreasing by a factor of 10. I start with a half, and I go all the way times 5 times 10 to the minus 18th. What we're doing, if we go back to the code, is I'm just taking the derivative of the sine function and using this symmetric formula, and then I'm just calculating it. The derivative of a sine is cosine, so the exact is cosine 1. I'm evaluating it at a point x equal 1. So you can see this is the exact value. It doesn't change. This is the calculated value, and this is the difference. Now, if you look at the difference, you see as we make h smaller and smaller, it goes all the way down, and this is the optimum value, like 5 times 10 to the minus 6. It's not the optimum value. It's somewhere between here and here. So if I went, if I went more, we'd probably get more zeros if I went to the value between 5 times 10 to the minus 6 and 5 times 10 to the minus 7 for h. But then you can see it starts to grow. So this is the instability. So you have to be very careful when you take derivatives using these formulas. Now here I put some formulas that are given in the book. You can derive these using more labor, take Taylor expansions to more terms, and the formulas get more and more complicated. But I just want to show you, just to compare them. Let's run this cell. Here's an output comparing a 3-point symmetric with a 4-point forward and a 5-point symmetric. And you can see how the 5-point symmetric gets down to almost negligible error much, much quicker than the 3-point symmetric. But it also has instabilities and starts growing. Now, if you use the SciPy package, it used to have a derivative function. It has all these other functions like integrations and special functions, a lot of stuff that I'll go over as I continue with these videos. But the one that they had for using the derivative has been deprecated. So if you were to try and use it now, you import, let's say, again, we're using the sine function. The exact is what's cosine 1, and now I'm trying to evaluate the SciPy using SciPy.miscellaneous.derivative. This is the function. You don't put parentheses here. You just put the function. This is where you want it evaluated, and this is your step or something. I'm not sure exactly how it works, and I don't care because we're not going to use this anymore. But when you hit this, if you evaluate it, you get the answer. You get cosine, and then you get the derivative, and you can see they match pretty well, though not exactly. They start deviating earlier. And then you get a deprecation warning, so on. It will be completely removed soon. And it gives you an advice to use either this, which I haven't looked at, but I'm not going to use because I was referred to this first. This is called Numerical Differential Tools, Numdifftools. And so that's what we're going to use. So you have to install this package. You can do it again through Anaconda. It's very easy to install an additional package. You can do it directly in a terminal using a conda or a pip. You get all kinds of problems when you switch between conda and pip and so on. So I'm not a programmer. And none of the programs I'm talking about or will show is they're like physicist programs. We don't comment them that much, and we just try and get the answer and hope that it's right. But we're not writing bulletproof, secure programs because we're not doing it for commercial reasons. We're doing it to learn. So over here, if you click on this, you'll get to the Numdifftools documentation, and you'll get to this page. And it talks about what is Numtools, and it's a suite of tools to do numerical differentiation in one or more variables. And it does it in an adaptive manner and Richardson extrapolation methodology. I'm vaguely familiar with these, but it's been a while. And it gets what they call a maximally accurate result. So a lot of the problems you have when you use your own formulas concerning instabilities and everything, they disappear when you use this. There are many options you can configure, and even besides derivatives, you have directional derivatives, gradients, Jacobians, Hessians, and all kinds of stuff. Now, they have tutorials. These things are mostly on how to install and so on like that. But if you go to how-to guides, Python and virtual environments and everything, that book I have talks all about this. But let's just go to the topic guides. And here you get the theory of numerical differentiation if you want to see what all this stuff is. And they sort of outline it. There are things with unequally spaced finite difference rules and various transformations of the functions, complex step derivatives. You can see it's higher orders, Richardson extrapolation methodology, and then it gives you all these examples. And so you can get a good idea if you want the background on the math. Then it has the reference of all the parameters and everything that you can use. But going back to my notebook, I just say there's an easy way to do it. And you import this package, and I'll call it ND so I don't have to type out Numdifftools all the time. It works on NumPy functions. You can put arrays and it gets the whole thing. Or you can, in this case, I'm just using a regular function from the math module of Python. Not the numpy.math, but just the math Python. And I'm doing the cosine one. And then what you do is you do ND dot derivative. You have to remember that capital D. That's kind of strange. Then you put the function in. You don't have to put in any other parameters. Just put the function in. I assign it to a variable called f prime. And then I evaluate f prime at the point 1. So it's going to get me that evaluation. Now, if you want more information, if you want to see what's going on under the hood, you can call it with NT derivatives, the function, and then full output equals true. And then you assign the value, this is a tuple, and the info from f prime 1. And now you'll get the same value as you did before, but now you can get an idea of what the error estimate is, what the final step is, and a lot of other things which I didn't show here. But let me just run this. So right over here, you see that we get the exact value, the Numdifftools value, and the error is about 10 to the minus 14th. And this says final step. I don't think that means it wasn't using that step all the way, but it's using adaptive steps. The final step was this. I'm not even sure what that means. So that's all I wanted to do today was to start. Next week I'll do numerical quadrature. And as I mentioned, outlined, this notebook is, it's only about 1/5 done. Actually, it's about 1/10 or 1/20 done. But I'm going to keep adding to this notebook, maybe once every few days. I'll do numerical quadrature next. And then we'll do how to find roots, you know, the usual Newton-Raphson method or secant method. And then there's NumPy and SciPy does, you know, much easier way to do it. And then we'll go to an example where we can get, I should add a space here. So these notebooks are not hard to edit on the fly. Let me just add, okay. And then I just put, it's very easy to use these notebooks actually. Okay, so semi-classical quantization of molecular vibrations, and then we'll do scattering by essential potential. Chapter 1 is only classical physics. Chapter 2 will go to doing how to do differential equations and solve them. And then we'll do some more classical physics, but we'll also, then in Chapter 3 we'll do solving eigenstates and bound state problems, and then we'll do more quantum mechanics. So I will see you next time. Thank you for watching. And I know it's been a while since I did a video. I will try and add to this playlist and also catch up on my group theory playlist. Thank you for watching.